Welcome to the Explainer. For decades, computers just got faster. It was like magic. But then they hit a wall, a hard wall. Today, we're breaking down one of the biggest, most important shifts in computing history, the move from making processors faster to just adding more of them. We're going to find out why your phone has more brains than a supercomputer from not that long ago.
So here's how we'll break it down. First, we'll talk about the good old days when software got faster all by itself, the so-called free lunch era. Then we'll see exactly what physical wall brought those good times to an end. After that, we'll explore the incredibly clever solution the industry came up with, the brand new, massive problem it created, and finally, we'll peek over the horizon and ask, what's the next great leap gonna be?
All right, so to really get this great pivot, we first have to understand a concept that basically defined the entire tech world for decades. It was called the free lunch, and it was an idea so good, we all just kind of took it for granted. I mean, you remember this feeling, right? You'd go out, you'd buy a new computer, and all your old software, your games, your applications, they would just run better. Everything was smoother, opened faster. It felt totally automatic, almost like a law of nature.
And in the industry, this had a name, the free lunch. See, for programmers, it was amazing. They could just write their code and then sit back and wait. Every year or two, chip companies would put out a new, faster processor, and poof, the software would get a huge performance boost totally for free without anyone having to change a single line of code.
But that era is over, done. The free ride came to a screeching halt, and it forced this radical, fundamental change in how every single computer on the planet is now designed. The big question is, why? What happened? Well, the end of the free lunch wasn't some business decision somebody made in a boardroom. Nope. It was a full-on battle against the laws of physics. Let's dig into the physical limits that brought this whole thing crashing down. Okay, so engineers found themselves stuck in this totally inescapable trap. For years, the trick was simple. Make the tiny switches, the transistors, smaller. That made the processors faster. But faster processors need more power, and more power creates more heat. And eventually, they got so incredibly hot that the chips themselves would become unreliable. Or worse, they could actually melt. So the old strategy, the one that worked for decades, just crank up the speed, it hit a literal wall, a wall of heat. You just couldn't cool the chips fast enough to keep going. That path to more performance, it was a dead end. So what do you do if your one engine can't possibly go any faster? Well, the industry came up with a new plan: add more engines. And this, right here, was the great pivot, a complete change in philosophy, from raw speed to teamwork. The solution was a concept called parallelism. The idea was, instead of pouring every bit of effort into making one single hyper-fast brain, or core, manufacturers started putting multiple, slightly simpler cores onto a single chip. First it was 2 cores, then 4, then 8, and now the numbers are just massive. Let me put it this way. The old model was like having one super chef in the kitchen who could chop vegetables at an impossible speed. The new, multi-core model is like having a whole team of really good chefs, all working on different parts of the meal at the same time. You can get a lot more done, sure, but it requires coordination. Now, this whole massive shift was really only possible because of something called the instruction set architecture, or ISA. You can think of it like a universal contract, or a translator between the software and the hardware. The software gives a command, say, add these 2 numbers. And the ISA makes sure the hardware understands what to do, no matter how that hardware is designed. This was huge because it meant companies could build these brand new multi-core chips, and our old software would still know how to talk to them. But, and you knew there was a but coming, right? This pivot to parallel computing came with a huge catch. It created a massive new challenge, and it basically shifted the entire burden for performance away from the hardware engineers and dropped it squarely on the shoulders of software developers. Think about it. Having a team of chefs is totally useless if the recipe is only written for one person to follow step by step. A program that was designed for a single core will only ever use one core, no matter if you have 8 of them or 80 of them sitting there doing nothing. To get any benefit from all this new hardware, programmers had to go back and rewrite their software, sometimes from the ground up, to split the tasks between all those different cores. The free lunch was officially over. And this wasn't some small technical hurdle, It was a monumental challenge for the entire industry.
As this quote from Steve Jobs really highlights, even the biggest minds in tech knew just how incredibly difficult it was to get software to actually use all this new horsepower effectively. Okay, so the pivot to multi-core literally defines the device you're watching this on right now. But even that approach is starting to face its own new limits. So the question becomes, what's the next frontier for computing power? As we get closer and closer to the physical limits of what we can do with silicon chips, the industry is looking for the next huge paradigm shift. And the answer? Well, it might be something that sounds like it's straight out of science fiction: quantum computing. The potential leap in power here it's just staggering. To show off what they could do, Google claimed its quantum machine solved a problem in just 4 minutes. That same problem, they said, would take the world's most powerful traditional supercomputer 10,000 years to solve. I mean, that's not just an improvement. That is a fundamentally different kind of computation. And that's because quantum computers take this idea of parallelism to a level that's, well, it's almost impossible to wrap your head around. Instead of 8 cores working at once, a quantum bit, or a qubit, can explore countless possibilities all at the same time. The potential processing power we're talking about here is so vast, it's just hard to even comprehend. So, the pivot from a single core to many cores was a revolution. It ended the free lunch, and it completely remade our digital world. Now, here we are, standing on the edge of what could be an even bigger leap, and that leaves us with one final question. What incredible new possibilities and what brand new challenges will this next great pivot unlock?